Hello, everyone, and welcome to today's public webinar with TPC Training entitled Understanding the Refrigeration Cycle as an HVAC Technician. My name is Ryan Smith, your host for the day, and our presenter today is one of our HVAC expert instructors. His name's William Smith, and he's going to be joining us here to tell us all about different aspects of the refrigeration cycle, how to understand different things like pressure and temperature and all the different components of the refrigeration cycle as an HVAC technician. So before we get started with this event, we are live here on this live broadcasting session, and with that comes an ability to interact with us while we're here together. So this is not a pre-recording, this is actually a live session we're in. So I want you to take advantage of that and feel free to ask us questions, and we'll be able to get to the questions at the end of the session. So if you see on your toolbar here, you should see a Q&A button. That's for our questions and answers. Feel free to type in a question into the Q&A folder, and we'll have William answer those questions at the end, as many as we can get to at the end. Also, I wanted to let everyone here know that this session is being recorded, and this recording will be available about 2 business days after the completion of this webinar. So be on the lookout for that. It'll be sent to the email you registered with this event for. And also, with that follow-up email, you'll see the PDFs of these slides we're presenting today as well for you to peruse and to share with your colleagues. So without further ado, let's go ahead and hear from Bill, and we'll learn a little bit about the refrigeration cycle. Bill?
Thank you, Ryan, and welcome everyone to our TPC presentation on air conditioning. I just wanted to touch base, and this is going to be a short presentation. There's no way to go over in 35 minutes everything about the refrigeration cycle, but Ryan will go over more with you later about how we can progress from there forward if you would like some more training in that area. So the basic refrigeration cycle has 4 major components. It's how air conditioning works. And then we're going to get into a little bit about what is superheat and subcooling, and how superheat and subcooling are the aspects that are important to make sure that we are using them to properly troubleshoot our system. We have no way of knowing whether our system is fully charged or not without using superheat and subcooling as our examples. Here's a basic refrigeration cycle. Now, this is starting out. We're going to get into more detail about what each component is doing. But as you see here, the evaporator is in your inside part of your air conditioning cycle. We're going to absorb heat from the conditioned space into the evaporator, and then using the refrigerant, as you see our cycle here, we're going to take it outside to our condenser, and we're going to displace the heat that we picked up inside of our conditioned space and displace it outside to a place where it makes little or no difference. So air conditioning refrigeration, again, transfer heat a place where it's not wanted to a place where it makes little or no difference. One key factor that some people don't figure in is humidity. It's taking humidity and heat out of the air what makes us feel comfortable. You could put cold air in a room and not feel comfortable if you don't get the humidity level down also. So there's no cold, but an absence of heat in the air that makes us feel cold. Cold is comparing 2 things. So if I was to tell everyone in this conversation today that 85 degrees is cold, most of you are going to say there's no way 85 degrees is cold. But when you compare 85 degrees Fahrenheit to 100 degrees Fahrenheit, we call 85 cold because it is definitely a colder temperature, and you can feel a difference between the temperature of being in a 100 degree environment versus an 85 degree environment. So picking up and following the heat is what the refrigeration cycle is doing for us. Taking the heat from the conditioned space and moving it to the refrigerant. And from the refrigerant, we're going to take it and move it outside. Then we have a couple options here. We can have an air-cooled condenser. We can have a water-cooled condenser, or we could have a cooling tower. All 3 options of what we're doing is picking up the heat in our conditioned space into our evaporator and displacing it outside. So what I'm going to do is a little bit here is to try to explain how the refrigeration cycle works and what are the most important aspects of when you are working with the refrigeration cycle. Starting out with thermodynamics, the 3 states of matter: solid, liquid, and gas. solid exerts pressure downward, a liquid exerts pressure on all sides, and a gas exerts in all directions. In our refrigeration cycle, we're taking that same refrigerant and we're recycling it over and over and over again, reusing it from a liquid to a gas, and then from a gas back to a liquid. What's important is how we're changing it from one state to another. The amount of heat that we add to that material is what's causing it to change from one state to the other. In the evaporator, we're taking a low pressure, low temperature liquid and absorbing heat, causing it to evaporate to a gas. Then all that heat we've absorbed into the evaporator, we're going to go ahead and give off to outside, causing that high pressure, high temperature gas to change back into a liquid. So we can reuse the refrigerant over and over again. The key with that heat transfer is the second law of thermodynamics. The second law of thermodynamics is that heat transfers from a hot to a warmer to a cooler place. So if I have a temperature of 75 degrees inside my conditioned space, and I have my refrigerant temperature at a low pressure, low temperature, I'm going to absorb heat into the refrigerant, causing the refrigerant to change state. So it's important to make sure that your evaporator temperature is less than the conditioned space. So that way the heat will transfer and absorb into your refrigerant. Then once we get the refrigerant outside, what we're doing now is we're taking that refrigerant and going the opposite of that. We have the refrigerant at a higher temperature and we're displacing the refrigerant to a cooler air outside. And as I referred to in that slide, 85 degrees does not seem like it's very cold. But compared to a refrigeration temperature of 110 degrees, that's going to allow us to give off the heat from the refrigerant to the outside and change the state of the refrigerant, causing it to condensate back into a liquid so we can reuse the refrigerant over and over and over again. So the refrigerant in the cycle never goes bad. It always is in there. And the only reason we need to go ahead and replace the refrigerant is if there's a leak in the system or mechanical failure. Otherwise, there's units that can last 30, 40, some 50 years with the same refrigerant continuously if they're maintained properly. Now, just want to touch base a little bit on how we size an air conditioning system. It's important to understand that you need a certain amount of BTUs of heat energy pulled out of a space to get us down to a comfortable temperature. Comfort cooling usually refers to a range of around 70 degrees Fahrenheit. Majority of us feel comfortable at 70 degrees. But again, making sure we're moving enough humidity, because if we're at 70 degrees and we don't take enough humidity out, we're still going to feel uncomfortable. So just kind of want to explain to you, ladies and gentlemen, what a BTU is in a actual sense. A BTU is the amount of heat required to raise the temperature of 1 pound of water 1 degrees Fahrenheit. So if I take a pound of water, which is approximately 1 water bottle, a water bottle in general weighs about 16 to 20 ounces. So that's a pound. And if I was to take a match and hold that match underneath the water, all that heat that's being absorbed into the water is causing the temperature of that to change 1 degrees Fahrenheit. For heating, that's what we're doing. We're adding BTUs of heat energy to raise the central heat temperature up of our conditioned space. But in retrospect, for air conditioning, we're doing the opposite. For air conditioning, we're taking heat out of the air, causing the air to come down cooler in temperature, and we're condensating moisture out of the air to lower the humidity temperature and humidity down. So BTU is what we're going to use to size our equipment. Now, a lot of you are probably confused on the terminology I went over so far. I understand that. This is just a general description of what the basics are of this cycle. So how do you size your units is important. So if someone comes into your house and they go ahead and they take square footage and they take into account your heat loss, heat gain, what do we need, how much BTUs heat energy do we need to remove from our conditioned space to make us feel comfortable? So when you go to buy an air conditioning system, instead of it being rated in BTUs, some of the larger systems are rated in tons. How'd they come up with that? They took a ton of ice and they figured out that it required 288,000 BTUs of heat to melt that ice in a 24-hour period. Since a 24-hour period is a long amount of time, they gone ahead and they sliced it and said, let's call it 1 hour. So depending on your square footage, depending on your heat load in your house, 12,000 BTUs is 1 ton of refrigeration. So if you had a 12,000 BTU unit, it'd be 1 ton. If you had a 3-ton system, you'd have 36,000 BTUs. So that's when you see your tonnage listed on your air conditioning system. That's what it's referring to. How many heat of BTUs we can remove from that conditioned space in a 1 hour's time. Obviously, the lower the BTU rating on your system, the smaller the room you can cool. The larger, the more you can cool. So is it better to have an oversized system? Not necessarily, because the temperature will pull down, but it will not take the humidity out of the air. So you want to try to size it as close to what you need as possible. So the 2 types of heat transfer from hot to cold that we're looking at, the first one's going to be sensible heat. Sensible heat is heat added or removed to cause a change in temperature. So what we're doing is we're adding heat to our solid liquid to make it a gas, from a liquid to a gas, or from a gas back into a liquid with sensible heat. We're getting it to a point where it's going to pick up so much sensible heat that it's full. So the 2 common numbers you're going to learn in school that you've learned in the past maybe is 32 and 100 and 212 degrees Fahrenheit. When we get to those temperatures, we're no longer sensible heat. Now at 32 or 212, we are using latent heat exchange. It's heat added to cause the change of state. And as I said, the 2 major things we're looking for in a refrigeration cycle is adding enough heat to change it from a liquid to a vapor, and then taking enough heat out to cause it to change from a vapor back to a liquid, and being able to reuse the refrigerant over and over again, transferring it from one state to another. Pressure affects the temperature. As we have more pressure in a system, we can raise the saturation temperature at which water begins to boil. But as we go lower in pressure and higher elevation, then we need less temperature to go ahead and boil our water. So we get along, and it's a little bit here, we're going to talk about our low side versus our high side refrigeration system, and why we want to lower it down to a lower pressure is because at a lower pressure, we have a lower temperature and we're able to absorb in heat. And at a higher pressure, higher temperature, we're able to reject the heat to outside. So just a small example here, what I'm talking about, atmospheric pressure decreases by a rate of 0.49 psi for every 1,000 feet in elevation. So if you were in New York City and you took a ladder and climbed straight up, if you went 5,280 feet, which happens to be 1 mile, you would be at 12.1 atmospheric pressure. Now, that being said then, remember, as atmospheric pressure goes down, the temperature goes down. So if I can boil water in New York City at 212 degrees, I need less temperature to boil water in Denver, Colorado. Approximately 205. I don't know, I'm not going to say an exact number, but it's definitely less because of the higher elevation and the lower pressure we have. So as I increase in pressure, I increase in temperature. As I decrease in pressure, I decrease in temperature. They work together. One goes up, the other goes up. One goes down, the other goes down. Now, the way we measure pressure in air conditioning is PSIG. If you have a set of manifold gauges, which is like a stethoscope, where you can look inside the system and see what your pressures are corresponding with, and then you take that pressure and we can say at this pressure, this refrigerant is this temperature. What they're doing is subtracting off the atmosphere. So if we go back a slide here a second, you'll see that if I had 16.696 PSIA in New York City, it would actually be 2 PSIG. But in retrospect, I would be at 14.1 PSIA to be at 2 PSIG in Denver, Colorado. I need to account for the elevation and the lower of the atmosphere. To convert between the two, we subtract off the atmosphere. So 0 psig, if you have that on your gauge, that's telling you that there's no pressure inside your system. All your refrigerant has leaked out, and you need to leak check the system to find out what's going on. Now, in the event that you are less than 0, you are in an absence atmospheric pressure called a vacuum. Two scales we use to measure a vacuum are inches of mercury and microns. So if you see a number on a scale or a gauge that says inches of mercury or microns, they're telling you that the pressure inside of that container is less than atmosphere. And if you were to open that container up, instead of pressure pushing out towards the atmosphere, pressure is going to absorb into the container because it's less than atmospheric. Example of that would be if you took a container that was in Denver, Colorado, and you went ahead and sealed it up, such as a pill bottle or something. By the time it got down to New York City, the bottle would start to collapse in on itself because it would be in a vacuum. That doesn't mean that we've lost anything inside of the container. We've just lost the pressure that was out in the container has less than the pressure on the outside of the container. And in a sense, we call that being in a vacuum. That's what we refer to a vacuum. So again, as pressure and vacuum affect saturation and vaporization and condensation temperature. Saturation is the temperature at which the refrigerant is changing state. Pressure will change that. So if I have less pressure, I can get my refrigerant to boil off quicker. If I have a higher pressure, I can get it to condensate faster. And we're going to distinguish between a low side and a high side of our system to make sure that we are getting the system to do what we want it to do. When you use your manifold gauges and you're reading pressure on your low side or pressure on your high side, you're actually reading the saturation is what you're reading. And you convert that to a pressure temperature chart, and you know that at this temperature, this is what my refrigerant is, and it's absorbing heat. So for example, your common temperatures for air conditioning are going to be about 40 degrees Fahrenheit on the low side versus 110 degrees Fahrenheit on the high side. Because of heat transferring from hot to cold, the lower temperature, lower pressure is going to allow us to absorb in heat to cause the refrigerant to change state. And when we get to the condenser, we're going to go ahead and allow it to give off heat to change back from a vapor to a liquid. So for those who've never seen refrigeration cycle before, here's a picture of the refrigeration cycle with our 4 major components. I'm going to take a little bit of time and go into detail about each component and what each component is doing in the refrigeration cycle. We're going to start with this one in blue right here. This is the evaporator. This is your indoor section. So I'm taking air that I want to condition and moving it across this evaporator, causing the heat to be absorbed into the refrigerant as a low pressure, low temperature liquid starting here. And as we see these dots flashing in here, that's the refrigerant flashing off and becoming a vapor. It's boiling because it's at a lower temperature. And as we change it, we're adding heat into the refrigerant called latent heat. Latent heat is what is the exchanging heat, and staying ice water stays at 32 degrees until at which point we have no more saturation of ice and water combined together. So here we have 100% liquid coming in. We have a mixture of liquid and vapor refrigerant going out until we get to a point where we have 100% vapor. Now, the key with checking your superheat and subcooling would be then taking this temperature here of the refrigerant, which it's saturated, versus the temperature at which we have for 100% vapor. The difference between the two is the amount of superheat we have in our system. Then our compressor is going to take that low pressure, low temperature vapor and cause it to be compressed. When you compress a vapor, it causes it to rise up in temperature. As it rises up in temperature, it rises up in pressure, and we push this high pressure, high temperature vapor into the condenser. And at which point it comes in as 100% vapor and starts to condense back into a liquid. Because it's a higher pressure, higher temperature, it tends to want to give off heat to the outside. So if we have 85-degree air coming across here, the 85-degree air is being warmed, being warmed by giving the heat to the air and causing the refrigerant to lose heat, causing it to condense back into 100% liquid. Now, when we have reached a point where we're 100% liquid, the difference between the temperature at which it's condensating versus the 100% liquid is our subcooling. So our superheat is found on the outlet of the evaporator, where we're adding heat to a vapor, and our subcooling is found on the outlet of the condenser, where we're taking heat out of the high pressure, high temperature liquid and cooling it down to a lower temperature. Now, our last component is our metering device. Now, our metering device is there to change the high pressure, high temperature refrigerant that's a liquid back into a low pressure, low temperature liquid. The condenser is there to take a high pressure, high temperature vapor and take and give off heat from the refrigerant, causing it to condense back into a liquid, causing it to change back into a liquid. The compressor to pump, pressurize the refrigerant, the key with the compressor is it needs to be in a vapor state. You cannot compress a liquid, but you compress a vapor. If you try to compress a liquid, so anyone on this call like to do a little science experiment, take some water and put it, in a container and try and smash it down to a smaller size. It's not going to do that. But you can take air and clap your hands together, and you can cause that air or vapor to make into a smaller space, such as a balloon. You blow a balloon up, you can take the balloon, squeeze it down, but you can't do that if there's water in that balloon. You're not going to be able to move it. And the metering device is there to change the refrigerant liquid back from a high pressure, high temperature liquid to a low pressure, low temperature liquid. Now, apologize went fast with that, guys. It's a lot of information in a short amount of time, but this kind of brings it all home right here. We're going to separate our system into two sides, high pressure and low pressure side. The low pressure side is where our evaporator is located. That's where we're taking that low pressure, low temperature liquid, and we're pushing it through this space, through the evaporator coil, and having air interact with this. And as the warmer air pushes across the evaporator, it's going to cause the refrigerant to change state from a liquid to a vapor. And once we've changed to 100% vapor, the difference between the temperature at which it's changing state versus the temperature of the vapor, that is my superheat. Once we have a low pressure, low temperature vapor, in order to give off heat, because of the second law of thermodynamics, we need to go ahead and raise the temperature and the pressure up of the refrigerant so it wants to give off heat to the cooler air outside. Again, cooler air outside, 85 degrees, 90 degrees does not sound cooler, but in retrospect, it is a cooler temperature than the refrigerant, which is going to be around 110 to 120 degrees vapor at that point. So the compressor pushes the refrigerant as a vapor, high pressure, high temperature, into my condenser. And the condenser now, once we have cooler air, which is 90, 85 degrees blowing across this, and our temperature of our refrigerant in the condenser is a higher pressure, higher temperature, we're going to give off the heat from the refrigerant to the air. So if anyone walks outside now in climate and goes ahead and puts their hand over their outdoor unit, they're going to feel a lot of heat coming off that outdoor unit. All of that heat is what's coming from your conditioned space and being pushed out of the refrigerant that's been absorbed in by the evaporator. Once we change it back to a high pressure, high temperature liquid, now all the extra heat that we give off in a liquid state is going to be our subcooling. So the difference in temperature between what we are condensing at, changing from a vapor to a liquid, versus the liquid line temperature is our subcooling. Once we have a high pressure, high temperature liquid, now we want to go back to converting it to a low pressure, low temperature liquid so we can start the process all over again. This is where our expansion device comes into play. Imagine taking a balloon and blowing up a balloon full of air and then starting to let air out of the balloon. We're going to have a high pressure inside the balloon versus the lower pressure outside the balloon. So that's what this is doing. It's a restrictor. It's restricting the flow of the refrigerant down and allowing it to expand out on the other side, so the pressure and temperature will fall. So in two spots in this system, we have latent heat. Latent heat changing from a liquid to a vapor, or from a vapor to a liquid, vaporization and condensation. And we have sensible heat. Sensible heat, again, is adding heat not for a change of state, but for a change of temperature. We want to raise the temperature up, so we compress our vapor and make it go up to a higher temperature. And then we take our liquid and we force it through a small opening, expanding it out, causing it to fall down into a lower temperature. So the refrigeration cycle is unique in that each one of these components is doing a separate part of the system. You have to have all four of these components in order for the refrigeration cycle to work. The heartbeat, the most important of all, is the compressor. Take the compressor out of the cycle, we don't have anything, because we're not pushing the refrigerant through the system and allowing it to do the changes we need it to do, picking up and giving off heat. But the airflow for the condenser and the evaporator, if we don't have air moving to our evaporator or moving away from our condenser, we're not going to pick up heat in our evaporator, and we're not going to give off heat in our condenser. So if you have a service call on a system and you're running a low pressure on your low side, your gauge is going to read about 70 psi G for R22 and probably like 400 for your R410A refrigerants. If you're lower than that, 90% of the time it's going to be because there's some type of airflow problem. So it's key thing, and we started out this conversation with follow the heat, picking up the heat in the evaporator, taking it through to the condenser, and giving off the heat to a place where it makes little or no difference. So the evaporator, again, we're taking warm air and forcing it through the coil. Because the temperature of the refrigerant is colder than the air going across it, the air is going to be, the heat's going to be absorbed into the refrigerant, causing the refrigerant to change state. Latent heat of vaporization. Saturated liquid in, superheated vapor out. And when we get to superheat, it's because once inside here, we got to the point where it's no longer a liquid and vapor mix. We're 100% vapor, and all the extra heat we're adding is our superheat, heat added to a vapor. Now for the condenser then, we're going to do the opposite. We're going to take a vapor in, and because the vapor temperature is high pressure, high temperature, approximately 110 to 120 degrees, depending if you're in Florida or if you're in Pennsylvania, other areas, you're going to have a higher temperature because you have higher ambient air. It says cool ambient air in. The word cool just means that it's colder than the refrigerant temperature. So we're going to take that 85, 90 degree air and blow it across this coil, and we're going to cause the refrigerant at 110, 120 degrees to give off its heat to the ambient air. And as we give off heat, it's causing the refrigerant to condensate. So we're taking it as a vapor and changing it to a liquid. And then once we get to 100% liquid, all the extra heat removed is going to be our subcooling. So follow the heat, ladies and gentlemen, is the most important thing you can remember. Taking heat from a conditioned space where we don't want it, and taking it outside and displacing it to a place where it makes little or no difference. So starting on our evaporator, picking up heat, going to our condenser and giving off heat, but using the same refrigerant over and over again to do the work for us. Now I'm going to spend a couple minutes talking about superheat and subcooling. And as Ryan will explain in a little bit, this conversation is just a tidbit of what you would see in our presentation, which is 16 hours. So I'm taking 16 hours of training and condensing it down into about 45 minutes. So bear with me with that, please. Superheat, again, it's found in the evaporator. It's heat added to a vapor causing an increase in temperature once we've gone above our saturation temperature. So saturation would be where we're changing state, and superheat is once it's no longer changing state. It's 100% vapor on the outlet of the evaporator. The extra heat we're adding is our superheat. Superheat is important because, as I said, you can compress a vapor, you cannot compress a liquid. So I want to make sure we have 100% vapor feeding into my compressor. Subcooling, heat removed from a liquid, causing a decrease in temperature. So what we're doing now is taking the condensing liquid, and once it's gone from being a vapor and liquid mix to 100% liquid, how much extra heat are we giving off? The reason we want to make sure we do that is because we want 100% liquid feeding into our expansion device. The expansion device wants 100% liquid feeding into it. If it's a mixture, it's not going to drop the pressure down enough to establish a lower temperature, lower pressure going into our evaporator. So this is how you would find the superheat and subcooling. You're going to take a gauge, and you're going to place it on the outlet of the evaporator, on the suction line, the vapor line, and that pressure is going to convert to our latent heat temperature. You see it here. Once we establish that we have that latent heat temperature, the difference between the latent heat temperature and the amount of extra heat added as a vapor is my superheat. Here we're showing you that we're using it for 10 degrees Fahrenheit superheat. It's not always going to be 10 degrees. It depends on your application. Superheat, you need to take into account your outside air temperature and your indoor wet bulb temperature. Wet bulb temperature takes into account your humidity. So we want to make sure we're getting enough humidity off. If we charge a system for the same pressures every time, regardless of what temperature it is outside, we have the possibility of putting liquid back on the compressor, and we've got problems. Now, for the condenser then, now we have subcooling. We start out with 100% vapor coming in. We reach a saturation temperature where we're changing from a vapor back into a liquid. We call that our latent heat. It stays the same temperature as long as it's a mixture of liquid and vapor going back into a liquid at this point. And then once we get to a point where we're 100% liquid, the amount of heat that we take out after it's 100% liquid is subcooling. So for this example, we're taking a manifold gauge, red in color this time, and placing it on our liquid line. And then we're going to get that 150 and convert it to an actual temperature. On a PT chart, it shows you that at different pressures, you have different temperatures your refrigerant's going to be at. And then once the refrigerant has changed 100% to a liquid, all of the extra heat removed is going to be our subcooling. So for this example, we're saying we're at 112 degrees Fahrenheit, saturation. That's we're changing from one to the other. And we're at 100 degrees liquid temperature, so the difference would be 12. Generally for subcooling, you're looking for anything around 8 to 12 degrees drop in temperature. The manufacturer will stamp it right on your data plate saying, hey, we would like to see this amount of subcooling for this unit. And that always manufacturer's recommendation is what you want to go by. If there's no manufacturer recommendation, 8 to 12 is a good guideline that'll work for you. Now, putting it together as to why superheat and subcooling are so important is a little chart I put together here for you guys. If you look and you see suction pressure versus superheat, which would be your evaporator versus your outlet of your evaporator, and your head pressure, which would be your condenser, versus your temperature of your liquid on the outlet of the condenser, you can see how different symptoms will give you different things. So by taking a manifold gauge set and hooking it up onto our system, we can use that to diagnose our system to see where our problems are at. Undercharged, we're going to have low suction pressure, low evaporator pressure, high superheat, low head pressure, and low subcooling. We're not going to have the 8 to 12 range we're looking for. We're going to be probably closer to 5 to 4. And if we're overcharged, we would see overcharged low superheat, but then our subcooling would be up now. So this is what I wanted to show you, is using all of these combined together will be able to help diagnose the system. When you walk out to an air conditioning system and try to diagnose it, you can't just hold your hand up to the air coming into your room and say it's cold. Cold to me is anything less than 50 degrees. Cold to somebody else could be anything less than 70 degrees. So remember, it's a comparison of two different things. So at this time, I'm going to turn it over to Ryan for questions. Ryan, are you out there, sir?
Yes, I sure am. Thank you so much, Bill.
Thank you, sir.
Yes, there's a lot of stuff happening here in the refrigeration cycle, huh?
Yes, sir. Yep.
So there's a lot of questions coming in on the line, and I would love to toss a few of them towards you, and we can chat about them. The first one I think I can take for us, and that is, are we getting continuing education certificates for attending this webinar? And unfortunately, no, we're not. This is just a kind of a free, public, openly available information session. So hopefully you are learning something and getting a cool little bit of some technical knowledge from this webinar, however. But here's a really interesting one, and here's one I always kind of leaves me scratching my head too. For those extra hot locations, Bill, in this case, Phoenix, Arizona. We have someone calling into this webinar from Phoenix, Arizona, and their question is, can the outside air temperature be actually hotter than the refrigerant temperature in the gas form, to the point where it could cause issues?
If the system's not charged properly, yes. But if it's working properly, believe it or not, even if the temperature in Phoenix is 110 degrees, the condenser coil temperature where it's condensating will have to be higher than that temperature. So depending location, what Ryan's coming to us from Chicago, I'm coming to us from Pennsylvania. If you're in a warmer climate, then your condenser temperatures will tend to be higher to accommodate for the fact that your ambient air temperature is warmer going across the coil.
Gotcha. So a proper refrigerant charge can counteract some of those extreme temperatures.
Correct.
Okay, yes. Gotcha.
Yes.
Cool. So something that always sparks my curiosity here is that superheat we talk about, that 10 degrees of superheat. That's actually pretty cold if we were to kind of use it by our typical means, where you're getting superheat, but it's in the 60s of degrees, and you're getting subcooled liquid, but it's 100 degrees. And it's just kind of amazing to me how something can be called superheat, but be kind of cool to the touch if we're actually feeling that line that the superheat is in. Always find that interesting. Let's see, we got a great question from someone asking about humidity. Just in a very general high-level sense, Bill, how is it that the humidity level of the conditioned air is regulated?
That's a really good question. That's where a lot of people get confused on, is if you look on a normal day, you'll see when you watch your weather, and they're going to say it's a percentage of humidity. It's 20%, 30%, 40%. And for those people who are in our, I know Pennsylvania is a lot of humidity. I'm not sure about other areas. So what I was saying is, if you have an area that you're in and it's 70 degrees outside and you're pushing humidity upwards of 50 or higher versus being in the same environment where you're at 70 degrees and at a lower percentage of humidity, you're going to feel more comfortable. The temperature is going to remain the same, but you're going to feel uncomfortable. And that's what we call heat index. So when you hear them say that it's 85 degrees outside, but it feels like 96, that's because the humidity has crept up, and it's probably like a good 70% humidity outside. Does that help, Ryan?
Yeah, absolutely. Kind of piggybacking off of that, some other questions about humidity in particular. How can really high humidity affect the cycle? Can it negatively affect the refrigeration cycle? And someone's asking, what if they do live in a humid place like Pennsylvania? What are some factors they can consider about tuning up the refrigeration cycle in their system?
Tuning up the refrigeration cycle, it'd be more of along the lines of making sure you're not oversizing your system.
Mm,
So when you do your BTU ratings, you don't want to, if it says, oh, I need 36,000 BTUs, and we talked about that 12,000 BTUs was 1 ton, and I said, I'm going to go with a 48,000 then, even though you only need 38,000. You're going to cool the temperature of that room down very quickly, and you're not going to get a humidity out of the air. So even in a 70-degree room, you can still be sitting there and have some nice beads of sweat coming down. And as far as the charge goes, that's where dialing a charge in using superheat and subcooling will affect that, because you need the right amount of refrigerant in there in your evaporator to make sure you have that latent heat exchange. If we have not enough liquid in there and we start to vaporize the liquid off too quickly, we're not picking up as many BTUs of heat energy. It takes a lot more BTUs of heat energy to change the state than it does to change the temperature.
gotcha. Thanks so much, Bill. We're getting some excellent questions coming in, and I'm going to do my best to filter through them and get as many of these answered as possible. So here's a really good question and a good challenge too, a kind of thought challenge here, and that is, you know, we're talking about coming out of that evaporator, a perfect gas, you know, that's 100% vapor, superheated. And this attendee wonders, well, that's definitely true if we're sizing it on design day, in the states would be described. What happens when it's not design day? How can one ensure that the compressor will see that perfect vapor when it's, let's say, a mild day outside?
We're going to take into account and do some things called low ambient conditions. So what we're going to do is we're going to go ahead and slow down the heat transfer on the outside section, so we're not making liquid as quickly. And we're going to do that with we're going to slow the fan speeds down. We're going to stop the fans. So an example of that from my personal experience, when I was in the Air Force, McGuire Air Force Base, we had a unit we put in that we wanted to run it 24/7, 365 days a year in a server room for air conditioning. So when it got to be colder temperatures outside, we were pumping refrigerant in there, trying to get our pressures up to where we wanted to be, because it looked like it was low on charge. And then by the time we got back around to the summertime, when it was higher temperatures, we had to remove refrigerant out. And we kept having to add and remove refrigerant until we added a fan cycling control, which was able to lower down the airflow going across there and maintain the difference between the high and the low side of the system.
Mm. Quick question for you, Bill, right here about superheat. Can superheat be measured across a compressor, or is that only from the evaporator leading to the compressor?
When you're actual reading it, you're going to read it from the outlet of the evaporator, from where you're switching. Now, you are going to raise up a little bit, and if on the refrigeration cycle, we call it de-superheating. You're not really using a measurement for de-superheating, and that would be on your hot gas line, which connection between the compressor and the condenser. It's going to give off a little bit. The main purpose of the superheat is there so that we get the right amount of temperature back to our compressor. If we have what we call a hermetic compressor, which is sealed, there's no way for that compressor to stay cool on a warmer day. So we're relying on the refrigerant to do that for us. But if we lower that superheat down too low, then we're pushing the liquid point where we're changing over to a vapor close to the compressor and having a possibility of getting liquid back to our compressor. So the answer would be, if you're measuring superheat, you're going to measure superheat exclusively on the low side or the inlet of the compressor, not the outlet.
Mm. There's a really good several questions coming in, but I will help answer a collection of questions of folks wondering if these copy of slides will be available after the session, and absolutely they will be. You're going to see a PDF copy of this information after the session, so to keep a lookout about 2 to 3 business days after this session is over for everyone registered for this event. The terminology there, Bill, condensing unit versus a condenser unit, is that the same thing?
Condensing unit is the compressor and the condenser combined together, but when you talk condenser and compressor, they're 2 separate sections.
Gotcha. So condensing unit is inclusive of that compressor.
Right. It's usually the
Got it.
compressor and the condenser all in one shell, but 2 separate components composed inside there.
Got you. Let's see. How about this one here? Will a clogged filter in our system cause a raise in pressure?
If the filter is used on an air conditioning system for the blocking of the air, filtering the air going to the evaporator, it'll cause a low pressure. If it's used for a heat pump, though, and that's kind of where the question, because a heat pump switches the cycle, then if you have in the wintertime high pressure then it would be because the indoor section is clogged. So it depends if it's a heat pump or but standard air conditioning system, the filter clogged will cause low pressure.
And this is a great segue, Bill. We've got getting a couple questions about heat pumps in particular. Can you describe what a heat pump is and how this refrigeration cycle might be different on a heat pump situation?
Here and do this. So where we said outside conditioned space versus inside conditioned space, what we're doing is just flipping the 2. So we're now making this the outside and making this the inside, and we're taking heat from outside and bringing it inside of our house. They're more conducive, better for warmer climates because once you get to a temperature, so the outside air temperature starts to fall down so low, the evaporator now outside, the temperature of the refrigerant has to be so much colder than the air that it's going to cause freezing on the coil. So the heat pump is literally, if you take a window air conditioner and flip it around. Window air conditioner, usually you're going to get cold air inside your house and hot air is going to be pushed outside. Just flip it. And you're taking heat and putting it inside of your house.
Oh, I never thought of it that way. Yeah, that makes sense. Then you're just putting heat in the house and cold outside.
Right. Well, you're not putting cold outside. You're bringing heat from outside inside your house.
Oh, I see. Yeah. The heat's coming from out to in.
What makes us feel cold, Ryan, is the absence of heat. So even when it's 35 degrees outside, believe it or not, there's still heat in the air. Not as much heat as a 70-degree day, but there's still heat in the air.
That's true. I think I learned from you, in fact, that there is no such thing as cold, is there? It's just the absence of heat. So it's whether there's heat there or not heat.
Right. Yep.
Got you. A great point, everyone. Thank you for these great questions. We're going to try our best to hit as many of these on the Q&A line as possible. We see some questions coming in the chat line. I'm trying to take the lion's share of what's coming in on chat and Q&A, but let's focus on Q&As, everyone, if we can. Here's a really good one for our folks on the coasts there, Bill. I see some folks are calling in from Hawaii and other places, California and the East Coast where you live. What effect can salt in the air make on the refrigeration cycle and the operation of an HVAC system?
The refrigeration cycle itself won't affect it, but the coils will take the hit. So, I mean, if anyone has a car and they know they're in salt water all the time, it starts to deteriorating the metals. So it'll cause your unit to leak faster because it's going to deteriorate the coil, but the refrigeration cycle itself wouldn't be as affected by it.
Ah, gotcha. That's a good point because that salt can really break down all sorts of electrical or mechanical equipment over time for sure. Question here about the heat pumps. Does a heat pump have an evaporator? And I would presume that it would, just in the different on the outside, right?
Well, a heat pump has both. The same what we're looking at here. I'll lift the screen up here. Is just taking this condenser and flipping it inside and outside. So what's happening with a heat pump is they work both the evaporator and the condenser inside outside coil can be the evaporator at any given time or the condenser at any given time. So it just kind of flips the refrigeration cycle. Not drawing this picture here, what would happen is we see where this line is connecting from the evaporator and pulling into the compressor, and how this line is pushing out to the condenser. So if I was to take that line and flip these two lines, so the compressor is pumping the same, only it's pulling in heat from outside and displacing the heat inside. That's how a heat pump works. It has an extra component in there called a reversing valve, which reverses the flow of the refrigerant from one to the other.
That was actually a question we got, then I think you helped with that. Someone who wanted to learn about reversing valves in the context of heat pumps as well. Awesome. Any other comments on those reversing valves before we move on?
Just that there a lot of problematic problems happens with that, and they're set up for two different functions. One, it can fail in heating mode, and one, it can fail in cooling mode. The manufacturers don't have them set up the same way. If you have a Trane air conditioning unit, it'll fail in cooling. So if it fails, you get cooling, you don't get heating. But for a Rood or a RUD system, a Rheem, you're going to get heating and you won't get air conditioning if the coil itself, the reversing valve, fails.
Okay, gotcha. I've got a really good question, a couple questions here, and I think this is going to be good for some discussion as well. Let's see. You definitely got some good questions answered about humidity. Here's a really good troubleshooting scenario, though, that I'm sure all too many of us have experienced as HVAC technicians, and that is on a chiller system in this case, but also throughout any sort of HVAC system, they had their lines freeze over, Bill. How would you try to determine the pressure needed on the inlet of these to prevent freezing over to happen?
You say freezing over as in the lines themselves going into the compressor freezing over, Ryan?
It would appear so, yeah.
Okay.
Or let's say even that the evaporator or any part of that cold side
Right.
freezing. How do we avoid that?
It's making sure your coil is clean and don't overcharge your system. Two reasons it'll cause it to do that. One, if that airflow going across this evaporator right here is cut down, I don't have enough heat to take this liquid and change it to a vapor. So all that liquid is going over here, and that's what will cause that line to freeze up. Because there's too much liquid going back. Overcharged will also cause that, because then we're not going to have enough heat absorbed into our refrigerant in the evaporator to cause it to change into a vapor. So it's two scenarios we're going to see where you would get, I call it frostback. That's literally what it's called. Freezing of your evaporator coil. Yeah.
Got you. Let's talk about that metering device on the other side of where the compressor is. That kind of lets us get to that low pressure. Does that TXV valve, does it ever get stuck? And can it be unstuck without replacement?
If it's a TXV, then what's happening is not shown in this picture. As I can bring another picture up that shows that a little better here. If you give me 1 second, Ryan.
Mm-hmm.
Thought I did, but yeah. So the TXV would be a device that's going to be put right here on the outlet of the evaporator. So it's going to go ahead and change the amount of refrigerant coming into our system. So you see right here where it says approximate point of last liquid and how much vapor we have. So I'm going to use this example and if in the event everyone in this call realizes that Will Smith is the presenter today and decides to pack into a room, then all of that extra heat load that's put into the room is going to cause that approximate point of last liquid to fall down here, and our superheat level is going to rise up. So the TXV is going to allow the refrigerant to be put in and keep it monitoring it at that point there. Can it go bad? Yes. And a symptom of that would be that the superheat is set for 10 and it's rising up too high. So what you would do is you take your bulb off of the evaporator and dunk it in hot water and watch to see if your pressures on your blue gauge of your evaporator would change. If it's not changing, then that means that that bulb has lost its charge. And once it's lost its charge, you're going to have to replace the whole metering device in order to fix the system then. Does that answer that question, Ryan?
Yeah, definitely. Got a great question from one of our attendees here. What's a better way to check the charge? Using gauges or using subcooling and superheat? And kind of to piggyback off that, should an HVAC guy use gauges every time he or she checks the unit?
To tell you, the best option is to try and diagnose everything you can without hooking up gauges. Now, but the absolute best way to check the system would be to hook up gauges and check your superheat and subcooling. They've come out with better gauges now. The problem is, for some systems, as a smaller refrigerator, smaller residential unit, it's designed, it has to have the critical amount of refrigerant charge there. So every time you hook up your gauges, you have potential of diminish releasing, or releasing the atmosphere, a little bit of that system charge and lowering it down. So to dial the system charge in exactly where you want to be, this is your option: superheat and subcooling, depending on what type of metering device you have. To diagnose your system, one small example, and if Ryan, you remember you were having issues with your air conditioning system, and I mentioned to you, if you take a thermometer and you put it on the return air of your ductwork, and another one on, or the same thermometer, move it to your supply or your ductwork, you should see about a 15 to 20 degree difference, drop in temperature. And that's a good sign that the system is charged close to where it needs to be. But to dial it in, the best option would be to use superheat and subcooling. So you're going to weigh the charge in, if it's empty, full evacuation, weigh the charge in, and then use superheat and subcooling to make sure it's where it needs to be. So it depends on the situation, Ryan, and what's going on.
Definitely.
There was training that they had years ago where we were taught to use our senses: touch, hear, feel. You know what I mean? If you don't feel cold air coming out of your supply vent, you know that there's a reason. Or if you don't feel any air coming out of your supply vent, then possibly your filter's clogged, or you have a bad fan motor that's not blowing air through your system. That's something you can diagnose without putting gauges on.
Awesome. I think we only have time for one more question, guys. Thank you all for being here, and thank you for your questions. This has been a really enlightening session, and can you believe it? We're almost at the top of the hour already, Bill. So I think I'll just take one of these other questions. And let's talk about types of refrigerants, alternative refrigerants, just to close out our session. 410A is the standard for residential and commercial applications in many cases. This attendee has a question about 407C refrigerant, and maybe you want to just provide a general comment on different types of refrigerant for, let's say, commercial and or industrial use, and what are your thoughts behind them?
Original refrigerants contain chlorine, and they discovered that chlorine was what caused the hole in the ozone. So they developed refrigerants without chlorine. So 410A, 407C are refrigerants that are considered HFC, hydrofluorocarbons. They don't have chlorine. The difference between those and like R22, which was our original air conditioning units, a lot of still R22 out there. The reason R22 was phased out was because it has chlorine. So 407C, 410A are replacements, but the key is every refrigerant requires a different type of oil classification. So if you have R22, which was an older refrigerant that contained chlorine, it would be an alkyl benzene. But when you go to a 407C, you would need a polyester. So it's very, very important that when you're switching from one refrigerant to another, that you make sure that the oil is compatible. Otherwise, you need to change your compressor oil to make sure it's compatible. And every refrigerant has a different pressure temperature relationship with it. So the reason why we have a flooded market with all kinds of new refrigerants out there is because in January 1st of 2020, R22 has ceased to be produced in the United States of America. So they're scrambling, trying to find a replacement for it because the cost is astronomical. It's going up. And Brian, you're familiar with that. You had a system which was low on refrigerant, and you had to add R22. So there is what we call a snap list out there. ASHRAE has put together a snap list to help customers and help technicians to know whether the refrigerant is approved by the Refrigeration Association, saying, yes, this is an acceptable replacement. But one of the key things I want to end on is that there's no drop-in replacement. So if you go from R22 and you want to change a system out to R410A, there's some adjustments you need to do. Same thing if you're going from R22 to R407C. It's still air conditioning refrigerant, but there's some changes you need to make in the system in order for it to operate properly. Ryan, was there anything else then, sir?
I think that's great, Bill. And I just want to thank you so much for being here and for telling us all about the refrigeration cycle. And I want to thank all of you for joining us today and asking some really great, curious questions about the refrigeration cycle here. There's definitely a lot to learn and a lot to continue to learn about. It's really a lifelong learning process when it comes to being a technical worker out there, especially in the technician space. You see different things at different times, and I hope you all found this really is a great way to get some of that great info on this. Now, still some great questions out there, and if you would like to ask us some more questions, we're available here at TPC Training to answer your questions. You can call our main line, and you can head over to sales@tpctraining.com, and you can talk to us about anything. We have a team of consultants ready to chat with you about any of the content we offer from this company that we can share and get you some really good training on. So with that said, thank you all for being here and have a wonderful day.